So man-made satellites. So in the video that we were just watching earlier, we were talking about what are these man-made satellites. Probably in science before, in maybe in geography, you have learned about natural satellites. Yeah. So a satellite is, just as a quick review, a satellite is something that orbits or goes around a planet. So something, so for our planet Earth, we have a natural satellite, which is the moon. That's an example of a natural satellite that goes around the moon. The moon goes around the Earth. Because of the pull of the Earth's gravity, the moon will just stay turning around and around the Earth. And within the past 100 years, some very smart people, some very smart scientists, they came up with the idea, let's make our own satellite. Let's make our own satellite to put in space and make it go around the Earth as well, just like the moon. Alright, and why do we make our own man-made satellites? Untuk hiasan? No, bukan untuk hiasan, but because when we put something up in space, we can use that machine for, or that space station for many different purposes. We can use it for research. So, for example, in the video dia ada sebut tentang Hubble telescope. So, apa dia buat? Basically, dia letak satu teleskop and satu kamera yang besar up there in space. And this telescope will send pictures to the Earth. And so we can use those pictures to know more about space. We also use it for communication. So, like right now we have internet. My computer is connected to the Wi-Fi. And this Wi-Fi is being sent through the internet. And this internet is being sent up into space, and there's a satellite up in space that takes the internet signal and then sends it to other places. Or same thing with your cell phones. There are satellites in the sky that takes the internet signal, the cell phone signals, and sends it to all the different places around. And so there are many things that these man-made satellites can do and are doing even right now. Google Maps. Those pictures from Google Maps are all taken from satellites. GPS, Global Positioning Satellite. So many things that satellites can help us do. So here's an example. Figure 3.33 shows the International Space Station, very famous space station, and also the MEASAT, MEASAT satellite. So the ISS can be seen from the Earth because of its large size and orbits at a height of 408 kilometers. So not really that far from the surface of the Earth. So we have the International Space Station, it's quite near, 408 kilometers. We have another satellite called the MEASAT satellite. This one is much higher, 35,786 kilometers above the Earth's surface. So satellites move in orbit at specific heights and suitable linear speeds. So when it comes to satellites, different heights will mean that the satellite will have to move at different speeds. So for example, the ISS or International Space Station, because it's lower, it's closer to the ground, it has to move at a different speed compared to, for example, the MEASAT satellite, which is much further away. Why? Well, we learned previously in was it topic 3.1? I think it's 3.1. We learned about centripetal acceleration, centripetal force. You remember that? So you remember that the centripetal force is what is keeping the satellite near or further away from the Earth. And so because the centripetal force is different, you need a different speed to balance the centripetal force, right? We learned that obviously the closer something is to the Earth, then the higher the centripetal force compared to if it's further away. And so these are the types of calculations that these scientists think about when we talk about satellites. Yeah, so formula for centripetal force and Newton's universal law of gravitation are used to establish and determine the linear speed of satellites. And so you can see in this picture the different things that they measure. It's not very... can I zoom in? So it's not very clear, but you can see in this picture all the different factors that they have to take into account. They need to take into account the distance from the center of the Earth, how fast the satellite is moving, and they have to balance it out so that they can maintain a proper orbit around the Earth. All right. So we apply these two. We have already learned in the past. We already learned about centripetal force, and we have already learned about Newton's universal law of gravitation. Sudah kita belajar dalam topik-topik yang sebelum ini. Right. So a satellite moving in a circular orbit around the Earth experiences centripetal force, which is gravitational force. Right. So we already know that. This is not something new. Okay. So because the centripetal force is the gravitational force, then we can say that these two are equal. So that's something very important bila kita buat kita punya calculations lah. Alright. So two formulas that we have learned before. So let me use the whiteboard for this. So this is how we use the calculation. So gravitational force the formula for gravitational force equals capital G. Remember, capital G is the gravitational constant. Okay, m over r square. Big M is the mass of the Earth. Smaller m is the mass of the satellite. Now the formula for centripetal force pula. F equals mv square over r. R being the radius. M is the mass. V square is the velocity. Now, going back to the sentence just now, it says here, a satellite moving in a circular object around the sun experiences centripetal force, which is gravitational force. So meaning to say, centripetal force is equal to gravitational force. So if we were to write that down, this force will be equal to this force. So we could do a substitution. So basically, gravitational force, let me use a shortcut. So gravitational force, I'll just use GF. Gravitational force has to equal centripetal force, CF. Formula for gravitational force is GM over R square. And since it's equal to centripetal force, we can say that it's equal to mv square over R. And by using this formula, we can use this formula to calculate many things. But usually we are going to use this formula to calculate the velocity or the speed of the satellite. So how fast does this satellite need to move? So if we were to rearrange this formula, so we can cancel this and we can cancel this. And so we end up with v square equals gm over r. We move over the square to become square root. So v equals square root gm over r. So that's how you come up with the final formula. So this formula is the formula that we're going to use a lot when we are talking about satellites. V equals square root gmr. Now you can, the solutions will be in the notes. So when I send you the notes, you will have the solutions in there. But I do want to show you how I do it step by step. Right? So yeah, this is what we just did. Okay, so since gm is constant, linear speed of the satellite only depends on the radius of its orbit. If a satellite is at a height h above the Earth, radius of its orbit r equals r plus h, r equals radius of the Earth. So GM is constant. Linear speed of the satellite only depends on the radius of its orbit. So what that means in simple language, yeah, the only factor for a man-made satellite on Earth, the only important factor is the radius of the orbit. We don't care about how heavy the satellite is. That is not a factor. We don't care about, well, we do care about the radius of the Earth, but the radius of the Earth does not change. The mass of the Earth, M, does not change. G, universal gravitational force, does not change. So the only thing that's changing in most of these questions is how far is the satellite from the Earth. So that's why we are using height. So we only care about the radius of the orbit. So radius of the orbit, R equals capital R plus h. H is height above the surface of the Earth. R is radius of the Earth, right? So therefore, we could substitute this R here with R plus h. Now, why is that? Why does this equal R plus h? All right. Remember, R is radius of the orbit. Okay, when we take the radius of the orbit, you have to start measuring from the center of the Earth. From center of Earth. For the radius of the orbit. Okay, so big letter R is radius of Earth. Plus h is distance from surface of Earth. Okay, we cannot just get the height or the distance of the satellite from the surface. You have to measure all the way from the center or from the middle. That's why we have to add. That's why we have to add these two, radius of the Earth plus height. Okay? Kecuali itu soalan dia bagi sedialah radius of the orbit. Kalau dia bagi sedia radius of the orbit, then no problem. Tidak payah lagi kamu kirain ni. Tapi kalau dia hanya bagi orbit of the Earth and height, then you have to add these two together lah. Before you can get the correct answer. Don't worry, we'll have some example questions later. So a man-made satellite can be launched to keep orbiting at a specific height around the Earth at radius of orbit R if the satellite is given linear speed v equals square root gmr. So this formula is very important. You can put, so basically what it's saying is this, you can put the satellite as near or as far away from the Earth as you want. And it will go around the Earth by using its gravity if you have the correct height if you have the correct speed at the correct height. So depending on the height of the satellite, as long as you have the correct speed for that height, that satellite will work. It will continue to go around the Earth. So for example, we have a GPS satellite here, which is 20,200 kilometers from the Earth. So here's the picture. So from the surface of the Earth is 20,200 kilometers. But remember, for us to calculate, we need the radius of the orbit from this small letter r here. So to get the total, we usually have to add height, distance from the surface of the Earth, plus the radius of the Earth itself. Barulah kita boleh dapat radius itu orbit. So you have to read the questions carefully lah. So in a stable orbit, like we said just now, linear speed of the satellite is v equals square root gm over r. This linear speed is high enough for the satellite to move in a circular orbit around the Earth. So centripetal, we already talked about this. Centripetal acceleration is the same as gravitational acceleration. Now, if the linear speed of the satellite becomes less than the required linear speed, so it's not going fast enough, then what will happen is because it's going too slow, it will, instead of going around the Earth, it will start to fall and get pulled by the gravity of the Earth until it falls away. Until it enters the atmosphere, and when it enters the atmosphere, it will start to burn up because of the air resistance. Okay, that is what happens when it's too slow. So, here's the satellite that we had just now. So let's calculate. Well, I'll just show you. Right? So we have the height of the satellite is calculated here. We change kilometers into meters. So we get a total of 2.02 times 10 power of 7 meters. And now we have to add the radius of the orbit. Sorry, we had to add to get the radius of the orbit, we have to add radius of the Earth plus radius of the height of the height of the satellite from the Earth. Radius of the Earth, kalau boleh kamu hafal. I think I've mentioned this before, but kalau boleh kamu hafal. 6.37 times 10 by the power of 6. Kenapa saya suruh kamu hafal? Because it's constant. It's not going to change, meaning to say most questions will use this number. Now, and I'm not sure, you might have a question di mana dia tidak akan bagi tahu kamu berapa radius. It will not tell you what is the radius of the Earth sebab dia mengharapkan kamu sudah hafal ataupun sudah tahu. So so make sure you remember that by now or by the time you have the exam, kau akan hafal itu. Okay, so how do we determine the linear speed? Well, we take all the information that we already have and we put it in the question. So, what is the information that we have? So, what is the linear? So, if the question asks linear speed of the satellite, all right, and this is the information given. So, if it gives you this information, so height is 2.02 times 10 power of 7 meters. Radius of the planet Earth, capital letter R, is 6.37 times 10 by the power of 6 meters. And then mass of the Earth, you should also try to memorize mass of the Earth, is 5.97 times 10 by the power 24 kilograms. And finally, we have the gravitational constant, G, which is 6.67 times 10 by the power of negative 11. As much as possible, try to memorize these three. Try to memorize the radius of the Earth, the mass of the Earth, and the universal gravitational constant. Anything that is constant, you should try to memorize as much as possible. Okay, anyway, so once you have this information, then we can try to find out the answer. So what is the linear speed of the satellite? Well, what's the formula of the linear speed of the satellite? V equals, we just learned it, V equals gm plus radius of orbit. But remember, to get the radius, we need to add the height and we need to add the height from the surface of the Earth with the radius of the Earth. So we can do V equals, so we can just put everything in the formula. So G, so 6.67 times 10. I'm running out of space here, huh? Wait, let me try and make more space. Let me write it down here. So V equals 6.67 times 10 power of negative 11 times 5.97 times 10 power of 24. I'm just using this formula. So gravitational and mass of the Earth over, we have to add these two. So height is 2.2 times 10 over 7 plus, and And I talk about this in the group. I sent this in the group, but in all likelihood, you'll have to use brackets. So I usually like to put brackets ahead of time, just to make it easier for the computer to for the calculator to calculate everything. Plus, sorry, where was I? So 2.02 times 10 power of 7 plus 637 times 10 power of 6. Okay, I'm not going to go through all the steps because it's already in your textbook. So I'll just go straight to the final answer. So your final answer will be 3.87 times 10 power of 3 meters per second. Meaning to say, what this question is saying, if a satellite is 2.02 times 10 by the power of 7 meters above the surface, then your satellite needs to be moving this fast. That's basically what this calculation is. And that's basically most of the questions for this topic 3.3. Basically, most of the questions will be, or a lot of the questions will be, if the satellite is this high above the Earth, how fast do you need to move? That's basically most of the questions. Okay. So there are different types of satellites. We'll go back to the formulas later. But first, let's talk about the different types of satellites. So there are two main types or two main categories of satellites. We have what's known as the geostationary satellites, and we have what's known as the non-geostationary satellite. So what's the difference? So we can see in this picture, there are different types of satellites. We have satellite A and satellite B, and both of them go around the Earth. But there's an interesting difference here. Satellite A, it says here, is always above X. So what does that mean? So here's the difference. So for a geostationary satellite, satellite is in a special orbit named the geostationary Earth orbit. So it moves around the Earth in the same direction as the Earth's rotation around the Sun. So if the Earth is going this way, then the satellite is also going in the same direction that the Earth is turning. All right. The second thing is the orbital period, or T, meaning to say how long does it take for the satellite to go to Earth, is 24 hours. Exactly the same as the period of rotation of the Earth. Meaning to say, when the Earth goes around one time, or when the Earth spins one time, the satellite will also go around the Earth one time. And the most important thing is this: it's always above the same geographical location. So what do I mean by this? What does it mean to say same geographical location? It means that even though the satellite is moving and always moving, it's always above the same place on Earth. So for example, if you have a satellite, dan satellite ini kita letak right above Tamparuli. Okay? Wherever Tamparuli is, the satellite will always follow and stay above Tamparuli. That's what it means to be geostationary. It will always follow the same place on Earth. So these are all so that's what we call geostationary satellites. So geostationary satellites have different uses compared to other types of satellites. So the other type of satellite is geostationary satellite. So it's either going to be higher or lower than the geostationary Earth orbit. Okay, and it's either shorter or longer than 24 hours to go around the planet. And basically, it's going to be above different geographical locations at different times. So, mungkin pagi, it will be above Malaysia, and then a few hours later, it will be above a different country, maybe above America, and then after that, it will be above Europe. So that's what we call a non-geostationary satellite. So these two satellites have two different types of uses. But they both still go around the Earth though. So they are both still orbiting the Earth but at different heights. So here's a comparison. It's not very bright. It's in your textbook, so you can check, and you can I'll send you the notes later so that you can see it better later. All right, escape velocity. So I think this is the last topic or one of the last topics for this part. So escape velocity. What is escape velocity? Escape velocity is the minimum velocity needed by an object on the surface of the Earth to overcome the gravitational force and escape to outer space. So meaning to say, the minimum velocity, escape velocity is you have to move at least at as fast as the escape velocity. You need to be moving at least this fast to go into space. If you cannot go this fast, you cannot go to space. That's basically what it is. So escape velocity, you have to be at a certain speed on the surface of the Earth to overcome. Meaning to say, kau kena cukup supaya kau boleh lawan dan larilah daripada planet ini. So if the object, so they gave us a formula here. So if the distance of an object from the center of the Earth is r, and the mass of the object is m, and the mass of the Earth is big letter M, the Earth possesses gravitational potential energy, which equals U equals GMM over negative G big M small m over R. So gravitational potential energy. So you learned about potential energy before. Okay, where something is not moving but it has the possibility of moving. And so for you to be able to go into space, you need to have energy that's greater than this potential energy, right? Figure 3.38 shows an object launched at escape velocity. This object can overcome gravitational force and move an infinite distance from the Earth. So an object that's moving has a certain amount of kinetic energy, 1 over 2 mv square. Right? So you have the gravitational potential energy, which is U equals G negative Gm over M over R. So escape velocity is achieved when the minimum kinetic energy is able to overcome its gravitational potential energy. In other words, if we were to write this out as a formula, what this sentence is telling us is this. Okay? So to achieve escape velocity, then the kinetic energy of an object must be at least equal, but probably going to be greater than gravitational potential energy. Okay, in other words, here's another way to put it. Gravitational energy is the energy that's keeping an object on the ground. Yeah, there's gravity that's working on it, and because of the gravity, there's potential energy that keeps something on the ground from escaping the planet. So in order to escape the gravitational pull, you need to have at least an equal amount of kinetic energy to overcome the gravitational potential energy. Then you can reach escape velocity. Bare minimum. So how do we calculate that? So basically, we can calculate it like that. So the minimum kinetic energy plus gravitational potential energy should equal 0. Or in other words, we could write it like this. Y equals 0. So kinetic energy, the formula for kinetic energy is this. Give me a moment, sorry. So this is the formula for kinetic energy, 1 over 2 mv square. So that's kinetic energy. Negative G mn over R. This is for gravitational potential energy. Kinetic. And this is gravitational potential energy. So I was just saying just now that to achieve escape velocity, this one must be at least equal to this one. And probably this one has to be greater than this. But the minimum, we use the minimum. So this one has to be equal to this one. So we can say we could rewrite the formula like this. So kinetic energy must equal 1 over 2 mv square must equal negative g m n over r. Or we could even write it like this. We could also write it like this. We could write it like this. Negative gm n over r must equal 0. Meaning to say this equals to each other. And so we could obviously simplify the equation. So if we were to simplify the equation, we could make it smaller and smaller. So when we simplify the equation, we get v squared equals 2gm over r. Finally, we get v equals square root of 2gm over r. So this is the formula that we use to find the escape velocity. Okay. Basically, as long as you know what formulas to use, as long as you know what the formulas are, you are able to answer the questions. It's all in the notes, so check in your textbooks later. Okay, so for example, here's an example. So if mass of the Earth is this and radius of the Earth is this, so we can calculate the escape velocity of the Earth using 2gm over r being the radius. So we use the formula. So 2 times gravitational constant, so 6.67 times 10 power of negative 11 times mass of the Earth, 5.97 times 10 power of 24 divided by radius of the Earth, so 6.37 10 by the power of 6. And you get a total of either 1.12 times 10 by the power of 4 meters per second or 11.12 kilometers per second. So in order to escape, if you want to build a rocket to escape the Earth, your rocket must be minimum be able to move at least 11.12 kilometers per second. That's the minimum requirement speed for you to escape Earth. So let's look a little bit into this now. What if we change some of the other things? So for example, what if we change the mass of the planet? If we have a bigger mass, what would happen to the final answer? Would the final answer get bigger or smaller? What do you think? If everything was the same. If v equals square root 2gm over r and we increase m, your final answer would end up being, your final answer would end up being bigger. So if we were to increase this number, if we were to increase the mass of the Earth, your final answer would be bigger. Meaning to say, the bigger the planet, the faster you need to be able to move in order to escape Earth. So that's very important if you want to explore. So this is something that you need to keep in mind. Yes, also because stronger gravitational pull. That's also correct. Bigger mass meaning stronger gravitational pull. Strong gravitational pull means you need to move faster to be able to escape the gravity of the Earth. Where was I? Yeah. So strong gravitational pull. So this is important if in the future, if we ever want to try explore other planets, even though I don't think that's going to happen very soon, but we can dream. If we ever visit other planets, you have to take into account, is this planet bigger or smaller than Earth? If it's a planet that's bigger, or not bigger but has more mass, mempunyai jisim yang lebih besar daripada bumi, then you might be able to land, but you might not be able to live because the escape velocity that you could use to leave the Earth might not be enough to leave this other planet. So you have to take that into consideration when you're exploring other planets. If it's a smaller planet or a smaller thing, like for example when you visit the moon, then it's no problem. If something can escape from the gravity of the Earth, then for sure it can escape the gravity of the moon. Okay, what about the radius of the planet? If we increase the radius of the planet but we keep the same mass, just the radius, what would happen to your final answer? Bigger or smaller? If we were to make the radius bigger, meaning to say you'll divide it by more lah, would we get a smaller final answer or a bigger final answer? Or basically, if you're having a harder trying to imagine, what's bigger? What's bigger, 1/2 or 1/4? Which one is bigger? Okay, so 1/2 is bigger. Meaning, yes, all right, very good. So, meaning to say, the smaller the lower number, when we're not talking about fractions, then the larger the final answer, right? Since 1/4 is smaller than 1/2, if we were to make this number r bigger, the bigger this number r, you actually get a smaller final answer. Right? So a planet that has the same mass as Earth but has a bigger radius, then it's actually going to be easier to escape. Yeah, like Emmanuel showed, 1/4 and 1/2. If you match the denominator and the numerator, you can see that 1/2 is actually bigger than 1/4. All right, so that's good. So now you know that there are different things that we can affect. All right, so benefits and implications of escape velocity. Okay, so we've learned about these things. So why are we learning these things and how is it practical, or how do people use this in a practical sense? Well, first one, the high escape velocity of the Earth. So as you can tell, it's not easy to escape the Earth. You have to be moving at least 11 kilometers per second. That's fast. All right? We don't have any car that moves that fast. If you could move 11 kilometers per second, you can go to KK in like less than 10 seconds. You know, if you go to Sandakan, if you're going 11 kilometers per second, it'll take you less than 1 minute to reach Sandakan. We're talking about something that's seriously fast. So it's really difficult to leave the planet Earth. Of course, humans have done it before, but it always costs billions and billions of dollars. That's why, yeah, it's hard to visualize it. You're right. It's hard to visualize it moving that fast. You probably have to experience it to be able to visualize it, because at that speed it's moving faster than sound. 11 kilometers per second is moving way faster than sound, which actually means dia limpas dulu baru kau dengar bunyi dia. That's how fast it is. Anyway, it's very difficult to leave Earth, which is in some ways a good thing. Why is it a good thing? It's because this means that Earth is able to maintain a layer of atmosphere, right? Any gas that's around the Earth, oxygen, carbon dioxide, and such, is not going to be able to move fast enough to get away from the planet Earth. So because of that, the oxygen and the air that we need will continue to stay as a layer of atmosphere around the Earth. Imagine if it was easy for the gas to escape. Habislah kita, tiada oksigen untuk kita bernafas. So that's a benefit actually for us. It also means that commercial aircrafts or fighter jets to fly to high levels in the atmosphere without possibility of escaping into outer space. Yeah. Meaning to say commercial aircrafts can fly at a linear speed of 200 So commercial aircraft, meaning to say airplanes yang kita selalu naik, can move at a speed of 250 meters per second, which is still quite fast, okay? 250 meters per second is 1 kilometer per second. 1 kilometer per 4 seconds. Quite fast. Okay? Not all, but some. We're talking about the fastest airplanes. I mean, fastest commercial aircrafts. Okay, your normal Asia plane is probably not going to move that fast. All right. Now, fighter jets can go up to 2,200 meters per second, or 2 kilometers per second, which is just crazy. But even at these high, crazy speeds, it's lower than the escape velocity from the Earth, which is a good thing because it means you're not going to leave the Earth by mistake. Right? If you're going too fast, let's say you're going 11 kilometers per second, then you might just it's possible to just leave the planet Earth by mistake and go into space. That's what we're saying here. But because planes can only move at about 250 meters per second and jets 2,200 meters per second, there's no chance of accidentally leaving the planet Earth, which is a good thing, like I said. Right, like I said, launching of rockets relies large quantities of fuels, yes, billions and billions of dollars to send one person to the moon. Right. And there are other things. Like when we explore other planets, you need to know what is the escape velocity of other planets and those kinds of things. All right. Solving problems involving escape velocity. You have calculated escape velocity from the Earth using the formula V equals 2gm over r. Yes, we just did that just now. We can also use the same formula to calculate escape velocity from other bodies such as the moon, planet Mars, and also the sun. Right? So, for a smaller and lighter planet like Mars, escape velocity is going to be lower. This is why the smaller planets like Mars and Mercury, they don't have much of an atmosphere. They don't have much gas or oxygen, if any, because it's easy for gas to escape. Right? The atmosphere on Mars is 100 times less dense than Earth's atmosphere. Meaning to say it does have some atmosphere, but it's not going to be enough for humans to survive. Now, on the other hand, a huge planet such as Jupiter, a very big and a very heavy planet, has such a high escape velocity that hot gases on its surface cannot escape into outer space. If you were to land on a planet like Jupiter, you better make sure that your rocket can go really, really fast. Otherwise, you're just stuck there. You're not going to be able to leave planet Jupiter. Right? So knowledge on escape velocity is important to determine how spacecraft can land and take off safely from a planet. Of course, we really aren't at that level yet. We haven't really visited other planets. The closest we have come to visiting is the planet Mars, but only a drone. We haven't sent like a human to Mars yet. Although Elon Musk seemed to think that he can do it. So we'll see. So, examples. The moon and the sun are two bodies in the solar system. Table 3.5 shows the values and the mass of the radius of the moon and the sun. So, it's asking you to compare the gravitational acceleration on the moon and the sun, and compare the escape velocity from the moon and the sun. So meaning to say, well, let's take a look at the table. So we have the moon, we have the mass of the moon, we have the radius, and we also have the sun and the radius of the sun. Now, just by looking at these two numbers, we can already tell that the moon is much, much lighter, has much less mass compared to the sun, right? The moon is only 7.35 times 10 by the power 22. The sun is 1.99 times 10 by power of 30. That's much, much bigger. Much, much heavier, I should say. And even in terms of the radius also, the sun is much bigger. Moon is only 1.7 times 10 power of 6. Sun is 6.96 times 10 by the power of 8. So the sun is both heavier and larger than the moon. But how does that affect the gravitational acceleration, and how does that affect the escape velocity? So these are all questions that we can calculate using formulas that we have learned in the past. So this is the solution, but let's go through it step by step together. So what is gravitational acceleration? We learned earlier in 3.1. Gravitational acceleration is calculated using G equals gm over r square. So for the moon, so we can calculate it separately. So for the moon, right, G equals, well, let's take a look. Where was I? Yeah, so G, remember G is always going to equal 6.67 times 10 power of 11. Ini tetap sudah, this does not change. So let's calculate for the moon. So 6.67 times 10 power of negative 11 times the mass of the moon. So what's the mass of the moon? Let's go back to that. So the mass of the moon is 7.37 times 10 power of 22. Right, so we'll put that back in the over, and then let's check the radius. So we're going to use the radius, and we have to square the radius. So what is the radius? So radius of the moon is 1.74 times 10 power of 6 square, just like in the formula. So once you have everything written out, we can determine that the gravitational acceleration on the moon is 1.62 meters per second. Okay, you can check the calculations in your textbook. It's all there. And so you can do the same thing for the sun. So let's try out the same formula for the sun. Okay, so for the moon just now we calculated it would be 1.62. So how about for the sun? So for the sun, again, same formula, G equals G, large G, 6.67 times 10, negative 11 times, what is the mass of the sun? We'll check again in the mass of the sun is 1.99 times 10 power of 30. Big number. And what is the radius of the sun? The radius is 6.96 times 10 power of 8. So once we finish calculating that, we put that in the formula and we calculate everything. You come with a final answer of 274 meters per second. Alright, so this is the gravitational acceleration of the sun. This is the gravitational acceleration of the moon. And as you can tell, just from these two calculations, the gravitational acceleration of the sun is much, much bigger. Right? So the question is, compare the gravitational acceleration on the moon and on the sun. So based on the calculations, the sun has a larger or greater gravitational acceleration compared to the moon. Okay, now what about the escape velocity? Obviously, escape velocity from the moon is going to be smaller than the sun. But by how much? We have to calculate again. Okay, so let me. So escape velocity is calculating using the formula V equals 2 square 2 GMR. We just talked about that just now. We calculated that earlier. And so we can calculate it for the moon. So you just put all the values in. So gravitational constant, mass of the moon over the radius of the moon. And you get the escape velocity of the moon is 2.37 times 10 power of 3 meters per second. Now for the sun, when we put in all the values and we find the final answer, it's 6.18 times 10 power of 5 meters per second. So once again, the escape velocity on the moon is much higher. Is much lower compared to the sun. The sun has a much greater escape velocity. So what this means is a ship that can escape the moon may not necessarily be powerful enough to escape the sun. Of course, a ship that can escape the sun has no problem escaping the moon, right? So don't use the same rocket that you used to visit the moon to visit the sun. Your rocket is not going to be strong enough to leave. Okay. Yeah, so like I said, the moon has low gravitational acceleration and escape velocity because the mass of the moon is smaller than that of the sun. The sun is the largest body in the solar system, yes, so gravitational acceleration in the sun and escape velocity is going to be higher, or in fact has the highest value compared with those of the moon as well as the other planets. So for this chapter, for Chapter 3.3, you need to know these things lah. Okay, so now we have finally finished up with chapter 3. Alright, so do you have any questions you would like to ask? Or some parts of the formula that you are maybe not so clear with? Or some other things regarding escape velocity or things of that nature? Or maybe something not so clear with the formula. So the only thing that is holding us back from further exploration is the speed of our spacecraft. It's not the only thing, but it's one of the things. There's a lot of things that's holding us back. Speed of the spacecraft is a big factor, yes, because actually let me put it. Of course, you need a spaceship that can move faster. That's one thing, but in order to move faster, your spaceship needs also to be stronger, because the faster you move, then the stronger your spaceship must be to be able to handle all that energy. And another thing is energy or fuel. We do not have enough fuel to send spaceships out into space. Like I said, it takes billions of dollars just to send one spaceship out to the moon, right? And most countries now do not have that kind of budget to send like rockets and what. And there's a limit. Also, there's a limited amount of fuel on the Earth. Like, even if we took all the fuel on the Earth, how far can we go with just the fuel on the Earth? Even if we were to use all the fuel on the Earth, there's only so far we can go before we run out of energy. So these are all things that are limiting us in our space exploration. Yes, you got to be rich to build such. Yeah, that's why the only people who are able to do this is people like Elon Musk. He's rich. Right? Yeah, and even if you're rich, how about technology? What do you mean about technology? What's the question about technology? So yeah, you do have to spend. You either have to be rich like Elon Musk, or it's the government that gives the money. So like a lot of the early American spaceships or like NASA and all that, that's government money, basically. That's basically government money that's sending, um, or that's funding these projects. So they had money from these projects. In Elon Musk, for Elon Musk, he's just rich. So he's basically building ships in his spare time. Basically, he's saying, "I have money." Elon Musk is basically saying, "I have money, so why don't I spend my money to try and build a rocket so that I can visit space?" That's what Elon Musk is trying to do. We don't have the technological capability to go to other planets for now. Um, the technology that we need to go to other planets is, first we need to find technology that will give us enough energy, so enough fuel, um, enough how do I say, enough fuel, enough energy to go from one planet to another. That's one. So that's one technological limitation we have. In terms of computers, we actually have, our computers are probably strong enough to go to other planets. Okay, imagine that spacecraft that NASA was using to go to the moon for the first time. That was like way back when computers weren't really that powerful, you know? Like they had a computer on the on that airplane, not plane, on that rocket. But like even my laptop is more powerful than that on the computer that they had on their rocket ship. I think the RAM that they had was like less than 500 megabytes, right? So it's not going to be a problem with the computers, but it's more of a problem with the materials to build the ship, the energy and the fuel to build the ship. Those are the main technological limitations that we have. And then the other thing is, if our spaceships goes really far away, how are those people going to communicate back to people on Earth? There's a let me stop